So what's our explanation as to why this hydroxyl group, this alcohol group attached to carbon number 2? That is how you know, but not the reason.
More electrons available?
Keep talking.
Is that carbon is holding more of a negative, positive charge than the other ones?
You just said the carbon's holding more of a negative positive?
I meant positive over negative, because the oxygen has 2 electrons that are willing to, they're more attracted to the positive there, rather than the other carbon, which already has 3 hydrogen electrons around it. Is that what, does it make any sense to you at all?
It's not, it's, no.
When you drew it, didn't you
Okay.
say there was, and I could not find, I did not write this down, so this is by memory and could be wrong, but it seems like we were saying there is 9 electrons attracting, and I don't know how we got 9, but where there was less on the end carbon than there was on the floating around the secondary.
So our 2 options, when this reaction happens, this H plus does what?
Breaks the double bond.
It breaks the double bond. And then what are your choices? Either of these 2, right? These 2 things that I've drawn here?
Right.
Either of those pop up. So this H plus came with a positive charge. So now what's the charge of this new thing that's got this H on it? Positive.
That has the extra.
I've got something that's got no charge on it, and on it I put something that's got a positive charge. This new thing that's been made has what charge? Positive 1 charge. So this positive 1 charge now needs to be stabilized by this propane, this hydrogenless propane molecule. Okay? All right with that so far? Everybody on board? So if this hydrogen went here, okay, or the hydrogen went here, those are our 2 options. It either went to the number 2 carbon or it went to the number 1 carbon. So if it went to the number 1 carbon, that means that this carbon right here, in its transition state, must hold on to a positive charge for, set period of time. Same situation over here, that this carbon has to hold on to a positive charge for a set period of time. Well, what are positives like? Negatives. So this carbon right here sees 1 electron right there, 4 electrons right there, and 4 electrons right there. 9 electrons. This carbon right here sees 1 electron there, 1 electron here, and 4 electrons here. 6 electrons. So the positive charge would rather be on which of the 2 carbons?
Secondary.
The secondary carbon, the one that's more substituted, for sure. So the reason that the OH is in that number 2 position is because the H picked, chose the side that put the positive charge on the more substituted carbon. Because this carbon here, this guy here, can sustain that charge, that positive charge a little bit longer than that one over there. So this water molecule, now we're to Jeff's explanation, this oxygen will be attracted to that positive charge. And now that those negative electrons, or those electrons that are on that oxygen, will attach to that, and then now that oxygen's got 3 bonds, and so one of the 2 H's leaves, which regenerates the catalyst that I started with. So what is this an example of? A Markovnikov addition. So this is a double bond, and I'm putting something across it. You guys should have done this. I'm sure all of you got that far with the balls and sticks last class period, where you had the double bond created, and then you disassembled the water molecule and added it across the double bond. So it's an addition reaction for sure. But it's an example of a Markovnikov. It's an example of a Markovnikov because the What happened to the hydrogen?
It went to the carbon with the most hydrogen.
They went to the carbon with the most hydrogens. But Markovnikov explained why this would be a plausible explanation, which would be that number 2 carbon is more negative, has more negativeness around it. It's an A, isn't it? Right there. I don't know. Okay, so right at the structural chemical equation, formatted like the equation above for the reaction of hydrochloric acid with 2-pentene. Okay, so I've got hydrochloric acid, and I've got 2-pentene, so I'll do, I don't know, a CH3, a CH2, a CH, I'll do a C with an H and a double bond, and a C with an H and a CH3. Yeah, there should be a cis or trans associated with that. It doesn't actually matter with this particular chemical reaction. You're going to get the same product no matter what. So what would we expect to get out of this? One, two, three. Oh, really? Did I really do that? I did that. I think that's like 2 days in a row. Are we okay with that? How I have that drawn? So the double bond broke, and then the H went to one and the Cl went to the other. So do I have another product? I'd get both of those. We okay with that? Which one do I have more of? You think?
The one on the end sticks out? No.
They're both what kind of carbons? They're both secondary carbons. So what's this?
Yeah.
It's a 50-50 mixture. So functional groups. So what's this? This one? This one? This thing? How about this? It's an ether. There's no E there. What else we got?
There's another ether up there?
Is there another ether up here? No, there's not another ether.
Oh, that's a double bond.
Yeah, if it was an ether, that carbon that's on the left would have a CH2 on it, yeah. So because that carbon only has, we know for a fact that it's a carbon chain, right? So that carbon must be bonded to 2 carbons. And since that oxygen is next to it, how is it bonded to the oxygen? Twice. I know it's bonded to the oxygen twice for 2 reasons. One, if it's not bonded to the oxygen twice, the carbon's missing a bond. And if the oxygen's not bonded to the carbon twice, the oxygen is missing a bond. So this one right here is a ketone. And this one right here, alcohol. And then a carboxylic acid. Okay. So what do we got for this first one? Great, 5 purple decking. This works a lot better without the tables. What do we got here? Next one? Next one? Pentel, yeah, good call, thank you, Pentel. Next one? And the last one? Okay. Complete reaction of 2-hexene and chlorine gas. So,
So in this one, you didn't say sister trans either. Or did you?
2, 3, 4, 5, 6. I only didn't, only because it doesn't matter for the reaction itself. So if I had a cis or a trans, can you tell me why it doesn't matter if I start with a cis or trans for this?
Once the double bond's broken, single bonds and it can all rotate.
Yeah. So either way, a cis or a trans, that double bond is breaking. And once it's broken, the whole cis or trans thing is out the window. We good with that? Draw.
Would you, put something over the arrow, like UV or something?
Sure, that's fine. It'll happen regardless, but UV will just make it happen more quickly. Is it the catalyst, UV? Energy in, right? The energy doesn't come back. So if you have something over the arrow and it's like 135 degrees Celsius, that's not a catalyst. That's just the environmental condition needed to have that reaction occur. 3 dice substituted. Okay. Sure. So good with the no. And we could do we could do okay. Do you guys have anyone do you want to talk about specifically? Okay.